We are going to start very soon as Shashi Bala ma'am will join us. Namaskar. I, Dr. Neha Agarwal, welcome you all on the fourth day of online lecture series, which is being organized by the Department of Chemistry, Navya Kanya Mahavidyalaya. As the convener, I welcome our today's valued resource person, Dr. Shashi Bala, who is from University of Lucknow, Department of Chemistry, University of Lucknow. And today's coordinator of the session is Miss Sadia Noor. Sadia, I welcome you for the session. Hand over to you, Sadia.
Yes, ma'am. Sure, ma'am. Good evening, everyone. I warmly welcome you.
Because switch on your camera.
Okay, ma'am. Good evening, everyone. I warmly welcome you all to the guest lecture series on Fundamental of Chemistry, organized by the Department of Chemistry, Navya Kanya Mahavidyalaya, Rajendra Nagar, Lucknow. It is my great pleasure to introduce today's guest speaker, Dr. Shashi Bala ma'am. Dr. Shashi Bala ma'am, working as Associate Professor, Department of Chemistry, University of Lucknow. She has completed their PhD in 2001 from Central Institute of Medicinal and Aromatic Plants, Lucknow, CSIR, New Delhi, and have more than 20-year teaching experience. She also available CSIR SRF scholarship. She published 5 book chapters, more than 30 research articles. Their research area is synthesis and characterization of nanoparticle and nanoposides and their biofunctional studies. Besides this, she is also working on carbohydrate chemistry. We are very happy and honored to have Dr. Shashi Bala ma'am with us today. Now, I request her to kindly begin the lecture and share her valuable knowledge with us. Thank you.
Thank you so much, Sadia, and thank you, Dr. Neha. Thanks a lot that just invite me for this series. I'm very grateful to you. And today's topic is for this lecture, because I know that this series is especially for the BSc students. So I have taken the topic coordination compound. The reason are so many. So before that, just a second. I'm going to share. I'm trying, huh? Just a minute.
Sure, ma'am.
I'm not able to share my.
I have made you co-host. You can share. आप वहाँ पे there will be icon share. You please click on that.
Should I send my PPT to you?
Yes, ma'am. Yes, ma'am. Please do that.
Then just a minute. Wait, please. Okay, just a minute.
Yeah, sure, ma'am. Ma'am, I have received your PowerPoint. I am just trying to download it and I'll start very soon.
Okay, thank you so much. Thank you.
Yes, ma'am. Now I'm sharing my screen. Ma'am, is it visible to you? Ma'am, please unmute करिए.
Okay.
Ma'am, PowerPoint is visible?
Yes, yes, it is visible.
Yeah,
So,
please.
first, I would like to say something about the topic, why I have given this topic. Actually, the coordination compounds are the compounds in which some covalent bonding, some ionic bonding that is present, and these compounds are very important compound because in our life, without this, our life is not possible. As we know that hemoglobin itself is a coordination compound, chlorophyll is a coordination compound, that there are a number of the compounds that are known, and that's why I have given this word a new word of the elements. So ma'am, what I will do, I will just say next, correct? So ma'am, please next slide. Yes. So at here that we can see here this is the coordination compound, and at here we can see that this coordination compound where this is the central metal atom, and this central atom surrounded by different atoms, that different atoms that may be neutral molecule, that may be negative ion, that may be the positive ion, and that are bonded by the donation of lone pair electron. That's why that is termed as the ligands. And what the donation, that is donation of the lone pair electron, actually termed as the formation of coordinate bond. So this coordinate bond is present in the coordination compound, and it is a complex compound. That's why sometimes it is also termed as the complex compound instead of the coordination compound. Next, please. Here, some terms are very important for this. That here are four different terms. That first is the coordination metal, second is the coordination sphere, third is the coordination number, fourth is the ligand, and one more word, that is the denticity. That is that also important. So first term, that is a central metal atom. Here we can see here at here there is this potassium is also a metal and iron is also a metal. Both are the element, but whatever the ion present outside this square bracket termed as the coordination sphere. Whatever the ion or the central metal atom or ion or this negatively charged ion that present within the coordination square bracket, that overall this termed as the coordination sphere. How many number of the ligands are present, that number of ligand termed as the coordination number. And this central metal atom, that may be a neutral atom, that may be an ion, that is termed as the central metal or ion. So one more term that is termed as the denticity. As we know that if we see any animal which actually depend on the, suppose there's a lion and lion depend on the deer, whatever the food he want, that one deer or some any vegetarian animals, then in that case what happens, that lion actually just catch their prey by their dent, by their teeth. So how many teeth he just nipped, that is responsible for the strength, for the how that lion has been keep that one. So here the same ligands, how many ligands from how many sides that ligands attached, that is termed as the denticity. About this denticity I will discuss more in our next slide, please. Here this is the ligands that ligands may be the neutral atom, maybe the maybe the neutral atom, maybe the ion. Like at here we can see there are this some ammonia molecule is here, there is the H2O molecule, there is the some chloride ion, there is the fluoride ion, there is the cyanide ion, nitronium ion, diazine, and so on. It means some neutral, some negative, some positive, any of that may be behave as a ligand. And at here, as in this case, this NH3, from this NH3 only nitrogen is responsible for the formation of the coordinate bond with the central atom. That's why this ammonia is termed as the monodentate ligand. In case of H2 only oxygen is responsible, in case of CO only oxygen is there, and in case of NO sometimes this NO behave ambidentate ligand. What is ambidentate ligand, that I will discuss later, but before that you should know that what is the monodentate ligand. So this monodentate ligand is a type of ligand where only lone pair, one atom is given their lone pair electron to the central metal atom. That may be neutral, that may be negative, that may be positive ion, and so. So this is monodentate ligand. Now the next one is the bidentate ligand. Bidentate ligand means, as I said, that in case of ammonia, yes, only nitrogen is responsible. But if ligand is this type of chain, this is a type of chain where this nitrogen and this nitrogen, both these two nitrogen are responsible for the formation of coordinate bond. That's why it is termed as the bidentate ligand. Dentate, that means from two sides, two teeth come to catch this metal. Similarly, at here this is the same one. This one is oxalate ion. Oxalate ion, we know, we actually analyze the oxalate ion so many times in our lab. And this oxalate ion, where these two oxygen atom, that these two oxygen actually gives their lone pair electron to the central metal atom. That's why that sometimes also from the chelate ring or the ring type structure, this is the cause of the chelation also. And at here, this is dimethyl glyoxime. Dimethyl glyoxime is also a bidentate ligand, where this figure I have taken from somewhere else, not of mine. So this is the simple one line definition is bidentate ligands are those ligands in which two atoms are ready to given their lone pair electron to the central metal atom, as we can see in this figure. Next, ma'am, please. This is tridentate ligand. In this tridentate ligand, at here we can see that here this is one nitrogen, second nitrogen, and the third nitrogen. These three attach here. So this is here probably metal is the present, metal, central metal atom or ion is present, and from three ends we have three lone pair electrons. This is the structure of idiochrome black tea. In this idiochrome black tea, actually three, one from nitrogen, second from nitrogen, and third from oxygen. From three ends, this idiochrome black tea can be catch any of the metal. And in case of the analysis of the hardness of the water, when we perform the experiment in the laboratory in case of BSc semester 6, actually this EBT is used there as a indicator. And this is EDTA. This EDTA is ethylene diamine tetraacetate. So EDTA is used as a complex agent, and here in that experiment, that's EDTA itself as a standard solution. In that hardness experiment, EBT first used as an indicator, EDTA as a standard solution. How much hardness is present? That hardness in form of calcium ion or the magnesium ion that is present in the water, that is the hardness of the water, and that get cached by this ligand, or first by this ligand and then later by this ligand, and the formation of sodium and formation of calcium and magnesium complex with this EDTA becomes colorless, and at the end point we get the blue color of this one. So it means this EDTA is also useful for the analysis of the hardness of the solution, estimation of the hardness of the water. Next, please. Another one is the ambidentate ligand. In this ambidentate ligand, actually ambidentate means if any group of atom which behave as a ligand can give lone pair electron from two sides, not only from the one side but from the two sides. Like in this nitro group, here this nitro from nitrogen, one nitrogen can give their lone pair electron, and this oxygen can also give their lone pair electron. Similarly, thiocyanide ion, in the case of thiocyanide ion, this thiocyanide one side from the nitrogen it can be attached, and from the sulfur it can be attached. And at here in the case of cyanide, the cyanide is also behave as an ambidentate ligand. So at so many times in case of the objective questions, it also come as a question that which one is the ambidentate ligand. So first, clear definition, you should know that what is the ambidentate ligand. Ambidentate ligands are the ligands which can be joined, which can give their lone pair electron from the both side, from the two side within the same molecule, within the same ion. Next, please. Now, next property is the chelation. Actually, what happened when there is the ligand is present and ligand is attached as in such a form with the central metal atom or the ion, so that they can form a ring. So when a polydentate ligand attached with the central metal atom in such a way that there is the ring formation takes place, and this process termed as the chelation. And because of the chelation, whatever the compound has been formed, that becomes stable. So this polydentate ligands are sometimes referred as a chelating agent because chelation happened in this case. The chelate effect is actually enhance the stability of the metal ion when it combine with the metal ion and form the complex compound. So this is the structure of the hemoglobin. At here, this is heme B is the monocyclic ligand. This is overall heme B is the ligand, where iron itself is the ion that is bind with this heme B, and overall the structure of the hemoglobin we get. Next, please. So, question arises that what is the main applications of the chelate compound? The main applications is that, as initially I was telling you, that there is actually number of the compounds are formed present nowadays in our daily life, in our body also, like in form of betel, that is actually cobalt, a complex compound of cobalt, hemoglobin in RBC where iron complex is present, chlorophyll where magnesium is present, and there's these three are actually present already in our body or in the nature. Metal poisoning case if happened. So in the case of metal poisoning of lead, copper, chromium, nickel, zinc, that can be removed with the help of EDTA, as already I had discussed in our previous slide, that how EDTA can form. EDTA, very strong, good ligand, hexadentate ligand can form a stable complex because of their 6 denticity and can be removed lead, copper, chromium, nickel, zinc if that is present in water in excess in our body in excess amount. So metal poisoning can be treated with the help of EDTA, and it is also a type of the application. Next one is the analytical chemistry. Now I'm coming on this how this coordination compounds are formed. So there are coordination bonds are actually formed, and the first theory was given by the Werner theory. Werner theory just given a little bit idea about it, that how this coordination bonds are formed. You can see here in the structure that some of them are the dashed line and some are the solid line. So at here you can see that here that first is the primary or the principal valency, that is actually a type of the ionizable valency, while the secondary valency, that is a non-ionizable valency. Whatever this dash line, that is a type of the primary valency, and we can say that how many charge of the charge, positive charge present on the central metal ion, that may be neutralized by the second primary or the principal valency, like at here. And in the first structure, 3 chloride we can see in by this dash line, while in the B structure 2 chloride are attached, while the third one is attached with this dot line as well as solid line also, while in the C 2 bonds combine as a secondary as well as primary with the chlorine, and while in case of this D, all the 3 are attached. And how it differ, that difference we can see with the reaction, that how these chloride are present. If that chloride ion present in the molecule, if that is present in the form of chloride ion, then the chloride ion will be treated with the silver nitrate and silver chloride precipitate will be formed. So we can see here 3 chloride are present. So 3 chloride will be give 3 silver chloride precipitate, 3 molecule of silver chloride precipitate when it is treated with the silver nitrate solution, while at here only 2, and at here no chloride, no precipitate will be formed. So all these can be compared with the help of silver nitrate solution, as well as one more, that here this how many number of the chloride ion is present. Similarly, the number of ions are also we can justify. So how the ionic conductance is, that ionic conductance can be calculated. So basically, ma'am, next please. So basically, what happened, ma'am? Just show me previous one. Actually, I think there is something happened. Next, previous. Next, just previous. Werner theory. Yes. So we can calculate the main application, main positive impact of this theory is that this, with the help of this theory, we can count how many number of the chloride ion and how the conductance is there, what is the color of the compound, that we can we get with the help of Werner theory. And that actually these are the point just for the support for the Werner theory. But there are so many side effects also. About the side effect, I will discuss later. Now, first, before that, we should know that what is the EAN, that is effective atomic number. Because Werner theory, that is related to Sedgwick theory. Ma'am, please next. Next, please. This Sedgwick theory, and Sedgwick theory based on the effective atomic number. Sedgwick theory actually just said that how much effective atomic number is present in any coordination compound in the central metal atom or ion. And if that effective atomic number is nearby the noble gas atomic number, then that complex salt, that complex ion will be stable, otherwise not. That is just the Sedgwick theory. EAN, that is effective atomic number, that we can calculate by this formula that is already I had given here, that that effective atomic number is equal to the atomic number of the central metal atom minus how many number of the electrons are lost during the formation of iron. Like here, I'm going to discuss about this cobalt ion. This cobalt ion, there's the 3 plus ion. So basically, the atomic number of the cobalt is 27, and the 3 electrons are removed. And here is the ammonia. 6 ammonia are attached. So 6 ammonia molecule are there. Each ammonia molecule given the 2 electrons. So total number of electron from the 6 ammonia molecule is 12. So atomic number of central metal atom minus number of electron lost in the formation of iron plus how many number of electron gained from the ligand, and the total is 36 in case of this example, and that is just shown. Yes, this atomic number is of krypton, that's why this ion is stable. Next please. In the next one, this is potassium. This is the formation of this is the molecule of potassium ferrocyanide, well-known compound. We use it this compound in test of iron when we do the qualitative analysis in our laboratory in BSc lab, BSc chemistry practical. And at here, this Fe2 plus ion, we calculate here En for the Fe2 plus ion in this molecule. So atomic number of the iron is 26. Electron lost when it is from 2 plus ion, so 2. There is a Cn is the 6, so 12 electron, and the atomic number is this. Now here this different examples are given. In case of this nickel tetracarbonyl, where my cursor, nickel tetracarbonyl, the oxidation number is 0, atomic number is 28, so 28 plus 4, and there is 0, so 36. So just for as example, I had taken all this just for the example that yes, if there is approximate atomic number, effective atomic number is nearby the this noble gas, then that coordination is fair, that coordination compound will be stable. But next please. But this is not always correct. Next slide please. But this is not always correct because there are so many compounds where a factor atomic number is not there. But instead of that, there is, yes, just a minute. Huh. This is the significance. What is the significance of effective atomic number? The main significance of effective atomic number is just understanding that effective atomic number helps in the formation of the coordination geometry, that the compound is stable or not, their reactivity, how their catalytic behavior. With the help of this, we get know. So this Wilkinson catalyst, it is by mistake it has been come. So for this, sorry, I'm for this. So the next one is the next one. Yes, these are the exceptions. As already I had told you that there are so many compounds where 36 is not present. Instead of 36, there is the 35 or 33 or 84 is present. You can see here the number of the examples are here. It is not necessary that if there is nearby noble gas configuration is not present, that ion will be stable, must be stable, and that is main exception. That's why Sedgwick theory was failed. So main Sedgwick theory just says how much effective atomic number is present. If that is nearby noble gas, then that is stable or not, and number of exceptions are also known. Next please. After this Werner theory, the next bonding theory is the valence bond theory. Actually, there are a number of the theories are known. One is the Werner theory, second is the valence bond theory, third is the molecular orbital theory, fourth is the crystal field theory, and so on. In my presentation, I have taken only two, just the Werner theory and the valence bond theory. And this Werner theory, after this Werner theory actually failed to describe so many properties of the compounds, that why some coordination compound shows the magnetic behavior, different magnetic behavior, why they show different colors, why some of them are not showing the follow the EN rule, though they are stable. That's why there is the need of the valence bond theory. So this valence bond theory actually based on some assumption, and the first assumption is that whatever the d orbital is present, that vacant d orbital And that vacant d orbital is always available just to catch this lone pair electron. This is the ligand which have this lone pair electron, and that lone pair electron donated to the metal, and that donated electron actually taken their space, their place in the vacant d orbital, and this is your vacant d orbital, so that they form this type of bonding. So this coordination bond is just the donation of lone pair electron, but that is shared between the two, one central metal atom and another with the ligand. That's why it is also termed as a type of a shared bond or the covalent bond also. When there is the mixing of the orbitals takes place, mixing means if there is the s, p and d orbitals are there, mostly in d block elements form coordination compound, not the s block element, not the p block element. Mostly d block elements form. And when valence bond theory, we go through the valence bond theory, the hybridization happened. And in case of when hybridization happened, actually s orbital plus p orbitals, s orbital as well as p orbital, both and d orbital also, they mix together. So whatever these vacant orbital, vacant atomic orbital, they mix together, that mixing is termed as the hybridization. And that after the hybridization, they form a new set of the equivalent orbital, and that new set of the orbital termed as the hybrid orbital. So after the, as per the valence bond theory, whatever the valence shell of the combining atom combined together, hybridized, form new hybrid orbital, and gives a definite geometry, and that geometry or the shape gives us idea that which can be the tetrahedral, which can be octahedral, which can be the pentagonal bipyramidal, which can be trigonal bipyramidal, and so on. This valence bond theory gives some idea about the shape and the geometry of the compound. So at here, whatever the number of the vacant s and p orbital, sp and d orbitals are present, this vacant d orbital always ready just to catch this lone pair electron, and then it forms this coordination bond. And whatever this hybridized orbital, that hybridized orbital actually just catch this electron. So this is not exactly the d orbital, vacant d orbital, but hybridized orbital. Bonding in the metal complex arises while when a filled ligand orbital containing a lone pair electron overlap a vacant hybrid orbital on the metal cation or the atom to form up the coordinate covalent bond. So as I said, that this is a type of the covalent bond because sharing of lone pair electron takes place. Next, please. Ma'am, next, please. Yes. So at here, there are the number of the ligands. As already I discussed, there are the number of ligands are there. And there are two type of ligands actually present. One category is the strong ligand, another category is the weak ligand. Strong ligands which have low spin, weak ligands which have the high spin. The strength of the ligand actually decided by the electrochemical series. Strong ligands are those strong ligands are those where, because of the presence of that ligands, pairing unpaired electron quite pair up and just leave behind their empty space for these ligands. So strong ligands, in presence of strong ligands, actually pairing happened, and in the presence of the weak ligand, no pairing happened. Because of that, actually we heard two terms. One is the inner orbital complex, and another one is the outer orbital complex. Inner orbital complex mean what the d orbital involved in the hybridization, that is the inner one of the combining atom. And outer orbital complex mean d orbital involved in the hybridization, that is outer one. That means whatever, suppose there is the 3d 4s2, then the next one may be when the hybridization happen, then maybe 4s 4p and 4d, all these orbital will be combined together. So in that case, if all the four, then that will be the outer orbital complex. Can you hear me? Because someone telling that, Neha ma'am?
Yes, ma'am, you're audible.
Thank you so much. Okay, so the next one, as it is given here, that the strong ligand have the tendency to pair up the d electron and the metal cation, and it provides the necessary orbital for hybridization. For hybridization, on the other hand, weak ligands does not have that tendency to pair up. That's why few strong ligands generally form the inner orbital complex, while the weak ligand form the outer orbital complex. So the inner orbital, it means n minus 1 d orbital. If involved, then that is the inner orbital. If n d orbital involved, then that is the outer orbital complex. And if unpaired electrons are present in the compound, because of the presence of the weak ligand, then compound will be paramagnetic. If pairing happen because of the presence of the strong ligand, then that compound will be the diamagnetic. And the magnetic character is decided by the calculation of the dipole moment. And there is the another method that how we calculate the magnetic moment of the there is another formula that magnetic moment calculated by a definite formula. That is another topic of discussion, so I'm not going to discuss that here. Next please. Here is some example I have taken because it is just I have very little time. So whatever I had given to you, idea about it, just the little bit idea about how many type of the hybridization can be happen, and that hybridization actually decide the shape of the molecule also. So the coordination number, if 2 is there, it means there is just a 180-degree present. Coordination number 2, hybridization will be sp, and no doubt geometry will be linear. So this is the example where linear geometry is present. If this is 3, it means there is the sp2 hybridization and the shape triangular planar. Nothing is new. Already we discussed about the geometry, about this hybridization in our earlier session. But what's new here, that what we have discussed earlier, as in case of the organic compound, that in the semester 2 and in semester 2 we have discussed about it, that there is a little bit about the hybridization, but that's examples are actually the organic compound. Here the examples are the coordination compound. There the coordination compounds, ion coordination spheres are present, and these are the various coordination sphere. As in case of here, this coordination number is 4. So coordination number 4, that means there's a sp2d. You can see here this coordination number 4 is there. So two type of hybridization happen. One type of hybridization sp3, then sp3 shape is tetrahedral and it is COCl4. But if it is same coordination number but hybridization different, sp2d, and the shape instead of this tetrahedral, now the shape is square planar. So here the shape is square planar. Now next another one, 4, if then it is sd3, instead of p involvement there is the d orbital involved, shape will be tetrahedral again, MnO4 and CrO4, that is. Next, if there is the 5 coordination sphere, the 5 coordination number, then or the 6 coordination number, various we get. It is dsp3. If it is dsp3, then it is trigonal bipyramidal, or it is dsp3 then square pyramidal, and 6 it may be the octahedral. Octahedral, if it is dsp3 or sp3d2, in the both case the shape will be the octahedral. So actually the shape or the geometry of the molecule of the coordination sphere depend on how these combined hybrid orbital are arranged themselves in the space. In three-dimensional space, how that arranged, the geometry of the coordination sphere will be present as it is. All the shape depend on the geometry. Next is the, after this geometry, the next is a wide word use that coordination compound, but number of the coordination compounds are known. So it is necessary that we should know that how we can name that. The name of this one is potassium ferrocyanide, but potassium ferrocyanide is general name. It is a general name. Their IUPAC name should be, we know, because this IUPAC name is the name that is known that is known everywhere, and this IUPAC nomenclature is very important because that by this IUPAC nomenclature, the compound will be known in all over the world. As you know, in case of same happen in case of organic compound also. So IUPAC nomenclature for the coordination compound is not as easy as in case of the organic compound. Here is little bit different. The difference is what? The first difference is that we take in first part coordination sphere if there is present, and another is the this ionic part. Besides that, if in the coordination sphere the central metal atom or ion is present, that central metal ion or atom or ion make it negative sphere or the positive sphere. If that is negative sphere, then the name will be different. If it is the positive sphere, then the name will be different. First rule is cation first, then anion. That is the first rule. And this rule, just suppose we say the NaCl, the name is the sodium chloride. Similarly, here is the potassium first, but it is the cationic part. And this one is your negative part. Now here, the iron is present. We can see here, this is the potassium, cationic part, and the rest. Now understand that this is rest is the negative part. This negative part is, in this negative part, iron is present. That's why we give the name ferrous, but not exactly ferrous, but it will be the ferrate, because as per the rule, if central metal ion is present in the negative sphere, then as the suffix arate is used, 8 is used. 6 cyanoion is present, potassium comes first, so this is the cationic part. Hexacyano 6 cyanide ion is present, ferrate. So hexacyanoferrate, this is here the full name, and this Roman number is the itself is the oxidation number or the valency of this iron. So the name for this is potassium hexacyanoferrate 2. Similarly, K2PtCl6, this is another well-known compound. Potassium cationic part, first name, then Cl6 hexachloro. Hexachloro, not chloride, it is chloro. Platinate, because platinum is the name, but because in the negative part, negative sphere, it is 8. So these are the some rules that you follow. First cation, then anion. Point out that which is how many number of the ligand is present, the same number, how many number of ligand is present in that, and if there is the number of ligands are present, then first give the number, then which ligand is present as per the alphabetically we arrange, as we can see here, Cr H2O whole 4 Cl2. So H2O, that is aqueous, that is aqua. 4 aqua is present, that's why it is termed as the tetra aqua. Then chloride ion, so it is chloro. Then chromium, overall because it is the positive charge. So chromium 3 chloride, not chromate. So these are the some rules we follow for the IUPAC nomenclature. These are some examples that is given here. Next, please, ma'am. So next is the isomerism in the coordination compound. As in case of the isomerism compound, in the isomerism, we know that what is the isomerism. We all know very well that what is the isomerism. Same form, same definition apply here also. That the compound which have the same molecular formula, but the different arrangement of the ligand in the surrounding, in surrounding the central metal atom or the ion, then this is termed as the isomerism. That may be there may be the molecular formula same, but because of the appearance of the ligand surrounding in 3D space or in the 2D space or in the joining, that are the two type of the isomerism, and because of that they have shown the maybe the similar or maybe the different physical and chemical properties. Coordination compound, as similar to the organic compound, they show the some difference and some similarities. So basically they are of the two type. One is the structural isomerism, another one is the stereoisomerism. The structural isomerism, that is there is the difference in the structure, and stereoisomerism, that means there is the difference in the arrangement of the ligand in 3 dimension. So in the structural isomerism, as this experience is shown here, this is cobalt, bromide, NH3 whole 5 sulfate. In this and this, these both are 2, but difference is this ionizable part is different. At here it is sulfane and at here it is bromide. So these two, though they have the same molecular formula, but because of the difference in the ion, they show different ionic test. This compound will give the sulfate ion test, and this compound will give the bromide ion test. Similarly, at here, This is the bromide ion and this is the chloride ion. So here this bromide ion given the test, and at here this gives the chloride ion test with the same reagent, that is silver nitrate. In this first one, in case of sulfate, we want the barium chloride solution, and for this we want this silver nitrate solution. But at here, both are the same, both can be treated with the same silver nitrate solution. But we know the color of the precipitate chloride is different than the bromide. Silver bromide is light yellow, and chloride gives the silver chloride white precipitate. Next, please. Instead, this solvate and hydrate isomerism is a little bit. Just a minute, please. Huh? Just a minute. Please, from where I will mute. I'm sorry. So this is the solvate and hydrate isomerism, and it is also a type of ionizable, but there is a difference. Here, this H2O molecule, as we can see at here, this is the H2O molecule. How many number of the H2O molecule is present? At here it is 6. And all the chloride ion just outside the coordination sphere, and the color is different. But if one of the H2O molecule instead of this coordination sphere, if it has come outside, then the color of this is get changed. Similarly, at here, this H2O, 2H2O molecule comes out, the color is green. So, because of the number of H2O molecule, the total number of atom is same in all the three, but color is different because of the difference in the number of H2O ligand which present in the coordination sphere or outside the sphere. That's why that it is a special type of the ionization isomerism. Next, please. Few other, that is linkage isomerism, there is the coordination isomerism, there is the ligand isomerism, and polymerization isomerism. Actually, these are the type of the isomerism. And the point is, if we go through this, we actually taken little bit more time. For the 45 minutes or the 50 minutes is not enough for this. So just I would like to discuss as in the linkage isomerism, as in the previous one, there is the linkage differ. Maybe chloride attached, maybe bromide attached, and so on. In case of the coordination, if suppose the two coordination sphere are present, so if that two coordination sphere present, then one is the chromium, another one cobalt containing. In the same case, because there is the difference in the central metal atom, the difference in the coordination sphere change, that is termed as the coordination isomerism. If there is a change in the ligand, then that is the ligand isomerism. And if there is the number of the polymer in a coordination sphere different, then that is the polymerization isomerism. So it is little bit about the structural isomerism. Now next is the stereoisomerism. Stereoisomerism. Stereo, as already I said, that stereoisomerism is a type of isomerism where all the ligands, as already I said, all the ligands arranged in such a way in 3 dimension that because of the arrangement in the 3 dimension that is different, they show the different behavior. As the first example is the geometrical isomerism. At here, cisplatin and transplatin both are known very well, but only cisplatin is used as anti-cancer drug, not the trans. Do you know why? The reason is because this is the cisplatin, and in this cisplatin, two chloride ions, these two chloride are attached, and when these two chloride comes near to the DNA band or the DNA strand, then that DNA strand, actually these chlorine actually removed, and that get attached with the DNA strand. That's why this cisplatin react with the DNA, and transplatin is not able. That's why this cisplatin used as an anti-cancer drug, but not the transplant, because of the special arrangement of this scene. Another example is this one, where this Ma4B2, the different compounds are present. There's the one example is Ma4B2 type of the compound. This is Ma4B2 type of the compound. Here it is the cis. In the case of cis, this B or B at the same side and all the A at the same side. Or you can say another method is this B at the same end and all that another end. So what this B? These B are the different. But at here, these be at the opposite side. These be at the opposite. That's why it is cis and this is trans. Cis and trans, already we know definition. So here is no need to discuss about it. Another one is the facial isomerism and the meridian isomerism. In case of at here, this facial mean one face is formed. This is one face. So if it is Ma3B3, three atoms are arranged in such a way that they form actually the one face of an octahedral, while if they form a meridian, then that is the mer isomer. So the face isomer and the mer isomer, that's our geometrical as well as optical isomer also. They show different optical activity. Next, please. This is the optical isomerism as facial and meridian already I discussed in the previous one. So again, it is a little bit clear picture at here. And at here, this is the cis form and this is the trans form. And that already I have discussed. Now these are the use how this coordination compound are used. So this is the uses of the coordination compound that can be used in the biological system. Already I have discussed this. Medicines, cisplatin, that as the diagnosis, galodium is used in the MRI, and ruthenium agents, ruthenium compound, that's are also used as a anti-cancer compound. Catalyst, as a catalyst, there is the Wilkinson catalyst is used. In the analytical chemistry, EDTA is used for the titration, for the quantification of the metal ion in case of the determination of the hardness. That metallurgy, hydrometallurgical process can be done with the help of this one, and in other, that is the water softening and the preservation of the organic substances and the photography. This coordination compound that is used very well. And nowadays, this coordination compound are really a part of our life in terms of medicines, in terms of essential compounds, and so on. So this is all about coordination compound. Thank you so much.
Thank you very much, ma'am. Thank you so much for this insightful lecture. मुझे लगता है कि हमारे बच्चे जो हैं फर्स्ट ईयर, सेकंड ईयर, थर्ड ईयर, कोऑर्डिनेशन केमिस्ट्री इज एन इंटीग्रल पार्ट ऑफ केमिस्ट्री and they all will definitely get a clear concept of coordination chemistry from now. And I now invite any questions, any queries if they have. If anyone wants to ask anything, they are most welcome to ask. Now I would like to invite Ms. Sadia Noor for a formal vote of thanks.
Thank you so much, Dr. Shashibala ma'am, for such a wonderful and informative session. We are truly grateful to you for sharing your valuable time, knowledge, and experience with us today. Your talk about coordination compound has been very inspiring and helpful for all of us. I would also like to thank our respected principal, organizing committee, and all the faculty members and students who joined us for this session. With this, we conclude today's sessions. Once again, thank you everyone for your kind presence. Have a great day ahead.
Thank you.
Thank you, everyone. Now, tomorrow we meet again at 5 p.m. Thank you so much.
Thank you, ma'am.